Hi Paul, thanks for attending this talk. Today I will talk about hardware isolation, about running a real-time operating system concurrently with automotive grade Linux on a Renesas R-Car platform. Some word about me. I'm Julien Massot. I joined IoTbzh company 1 year ago as a Linux developer and a Zephyr specialist. I used to work on a Yocto operating system for the humanoid robot market, but I worked for 10 years managing a Linux operating system. Some word about the IoTbzh company. We are almost 30 engineers dedicated to embedded Linux and the AGL frameworks. Our goal is to deploy AGL in cars and boats. We had a first success about doing a delivery for the maritime market of an automotive grade Linux based system on a specific distribution, which is done internally at IoTbzh, which is RTOS, which aims to be AGL with a long-time support. We are located in French Brittany, in Lorient, which is just close to the sea. Some word too on the RTOS architecture. RTOS aims to cover all the sensors to the cloud and with Linux, of course. My talk will be most on the Zephyr environment and real-time operating system, but on other talk with Vincent or José, we will also speak about how to manage cloud connectivity and how to do messaging between all these components, between Linux component, real-time operating system, or even how to push the messages or get the messages from the cloud. So today's agenda, we will first talk about what is hardware isolation, and also some words about what is a coprocessor, but that can be found on a recent system on chip. We'll also introduce the Zephyr real-time operating system in automotive grade Linux environment. Also, an important point is how to communicate between both worlds. So that's why this talk is about a real-time operating system within automotive grade Linux environment. Also, some word about how to manage this coprocessor and real-time operating system from the Linux, and some word about what we will do next at IoTbzh. So first slide is what is hardware isolation and how we can compare it with other isolation technique. So on the left side we have hardware isolation. So basically it's running another real-time operating system on another hardware and processing unit. It may share some RAM area to do communication or share for general shared memory purpose, but doesn't share anything either from software point of view or hardware point of view. So we have dedicated resources and we can really understand how our system will run. Just after we can see hypervisor, which go to the same goal, so isolating components and have a better understanding of how our component will run. It's almost the same thing, but it will share some hardware parts. It can be CPU or some I/O or even RAM or memory. More close to the application, we have a host container. So in this case, we will run different Linux operating system or operating system running on the same Linux kernel. So they will share the Linux kernel, and then we can have one environment or another environment for the application. It will run a total system with an init system like systemd, which will start daemon and process. And on the right side, we have the desktop container, which aims to run application in a specific library environment. So the goal is more to make them compatible across different operating systems and have the same binary running on different environments. In this case, they share the Linux kernel, but may also share the operating system libraries. That's it. So this talk will be about hardware isolation, which share almost no software resources or hardware resources with Linux environment. So now, how you will do isolation about your safety task. Hardware isolation means that you will dedicate hardware resources. So you will choose which CPU will be dedicated to this safety task, which peripherals, that can be USB, I2C, or even some buses, and dedicate some part of the memory that will be not accessible to the Linux environment. We do that to have a predictable safety task, so we can really understand, have deep understanding of what will happen on this safety task and what external elements can influence the execution of this safety task. One of the goals is to reduce the attack surface of your software. You have isolated your software, your hardware, so you can really understand how an attacker can reach your software. In the end, we will have 2 or more operating systems which will run on the same system on chip. One of the goals can be to be able to certify your safety task. This is one point which can be complicated, let's say, with a Linux environment where you have to explain all your Linux environment is working, and perhaps you don't have a full understanding of each line of code is running on your rich environment, like automotive grade Linux, when you can have a big Linux kernel and let's say hundreds of different packages which is pulled from the auto. And at the end, you most likely want to communicate between both ones, because you most likely dedicate hardware resources, and perhaps there is some interesting information that can be extracted from their resources that may be relevant for even Linux or pushed to the cloud. So, what this real-time operating system will run on a processor. So we'll talk about coprocessor. So what is a coprocessor? A coprocessor is a physical component unit. So a CPU, it's a physical one, not a virtual one. It may not run the same operating system. So if it's a microcontroller, most likely we will not run Linux on the system. Even if it's possible, we may want to run a smaller operating system. Or even no operating system at all. It can be bare metal software that we want to run on this MCU. They may not share the same architecture. So that means they are not binary compatible. So you can't just move one software to another computing unit and hope it will run on this operating system. You have to choose a different compiler, and see how to compile your application. Most likely, this coprocessor will handle a very specific task. It may be your safety task, a really specific application. Often in a modern system on chip, coprocessor used to handle radio like GSM or even sometimes Wi-Fi. It can be video processing to do video encoding, which is you can have coprocessors which are more efficient to do this task. Coprocessor often also handle audio processing. Take for example audio wake up warn to when you want that your main system will be woken up by a word. Often now modern SoC integrate neural network computing unit. And in our case, most likely it will be about safety application. So let's have a look at the architecture of a Renesas R-Car H3 system on chip. So what we have on the left is the usual Cortex 8 processor that we use to run automotive grade Linux on it. At the bottom we have all the memory or I/O devices that you use to communicate with the car environment. What we often don't see is that there is another computing unit that we are not using. That's the Cortex R7, and that's the subject also of this talk. So what is this Cortex R7? This Cortex R7 is general purpose microcontroller. So it means it can handle various tasks, not specific to video processing or what we can have with DSP, for example. It's not already affected to audio processing, video compression, or already affected to a task within our automatic grade Linux environment. It can access any memory map device, so all the devices we saw in the previous slide are accessible from this processor. It's just a matter of choice if you want to handle it from this processor or from Linux processor. It's an ARM-v7, so it means that it's a 32-bit microcontroller. It will not be able to run binary which are compiled from ARM-v8 binary that we run on Linux. 800 MHz, so it's already a powerful microcontroller that can handle a lot of tasks. It has dual core lock steps. So dual core lock step means that in reality we have two CPU units, but in this case they are running the same task as a matter of redundancy. So it may be really suitable for safety application which require redundancy even in the computing unit. It has a GIG interrupt controller, so that's the generic ARM interrupt controller, so it can handle a lot of interrupts, and very flexible and often integrated in a real-time operating system. So that's cool. That's enough to run complex tasks, and really can be considered to offload some safety tasks from the Linux processor to this system. So okay, now we have an idea of which CPU we want to target for this safety task. So let's think about which real-time operating system we'll choose to run on this computing unit. Since we used to use Linux, most likely we will go for a free and open source software real-time operating system. We most likely want to have a comprehensible documentation to go fast on other system. if possible, a dynamic community, as we are used to have on automotive-grade Linux and Linux environment. And yeah, we are Linux developer, and microcontroller world tend to be different, so we may want to choose a real-time operating system which doesn't have a high cost to go for a Linux developer, and so that will be easy to handle to someone which is used to Linux. If possible, we also want to have POSIX compatibility, so that's very convenient. So if there is already a library that is interest for us, but we want to integrate in this application, it will be easier to integrate it within this real-time operating system. So let's go for Zephyr project. So the Zephyr project is a real-time operating system which is appropriate for a microcontroller. It started from RTOS Project, which was named RTOS. That's a Linux Foundation project. It aims to have a small kernel with many protocol stacks which are already implemented, like networking stack or CAN bus stack, which may have interest for automotive-grade Linux. One interesting point is it has unaudited code base. So since the beginning of this Zephyr project, the goal is to have a real-time operating system which is possible to certify. Also, it has long-term support, which is important for the automotive market. We have a security update. It has a permissive IoTbzh 2.0 open source license, and is very dynamic. Have many contributors and sponsors like Facebook, Google, Intel, Nordic Semiconductor, NXP, or even Lenovo. So, how you will do to run your application on Zephyr? You have to see which hardware part of your system on chip you want to dedicate to Zephyr. Then let's see if your platform is already supported by Zephyr. That's possible, or you may have to port some driver or do some hardware integration. After, as usual on Linux, you have to describe your board or development board using device tree. We hope you will be able to reuse some hardware driver that may be already there, like CAN bus or Hyper-C, and reuse some high-level operating stack services like Bluetooth Low Energy or CAN Open Protocol, or even MQTT if you want to talk to the cloud from your Zephyr application. Then you are ready to port your safety application. So here we are. We finished to do the hardware port and your application port. So we are really happy we succeed to do hardware isolation. So we have on the left side our Zephyr application and in the right side Linux application. That's great. But perhaps that's too much. But perhaps that was not exactly what we wanted at the beginning. Perhaps we want to make bridge between these two worlds, because it's not running Zephyr and AGL, it's running Zephyr and with AGL. So let's introduce some communication techniques. So both CPU have access to the same RAM and can post message. And hopefully there is already a protocol which is named OpenAMP, which allows to communicate between a host processor and a coprocessor. That's what we did at IoTbzh on this Renesas platform. We make use of this library to be able to share buffer and messages between these two systems. So we have our critical application that may want to notify Linux about, let's say, something which happened on the CAN. A door is open or any information that may be relevant for the end user. So we will be able to post a message on a shared memory and send it to Linux and notify it using interrupts. So let's have a deeper look about how works this protocol. On the left side, we still have our Zephyr environment, which will run Zephyr services which have information that may be relevant to Linux. It will make use of the open source OpenAMP library to post messages in a RAM area. We already defined a shared memory area, and we post message. It will then make use of an hardware blocks, which is used to trigger interrupt from one side to the other. So it's a bidirectional interrupt module, so Linux can interrupt the Zephyr, and Zephyr can interrupt Linux to say, hey, you have a message to read. Hopefully in Linux it's already supported using the RP message framework and the virtio framework. So that's a virtual bus, but it's already in use also in emulation technique. So okay, we are able to share buffer between both worlds, but that's not as convenient as we used to have in automotive grade Linux environment. We used to have services which are convenient to call from an application. We just have to call this binding and get the return of this function. That's most likely what we want to have in this architecture. So we are working on a component which is called Microbinder, which aims to connect this Zephyr environment to our automotive grade Linux to have a smooth transition for application which may call this API. So in this way, you will be able to have the same application, but with the services which may be running on one environment, which may be Linux running on Cortex A processor, or these services, depending on the platform, may run on a Coprocessor, which run a different real-time operating system, in this case Zephyr. So the goal is to make the binder able to use the previously described OpenAMP protocol as a transport at the same level that we already do for a WebSocket transport or TCP transport. Okay, so we make run our application on Zephyr, and we are able to communicate with our Linux environment. Let's have a look at how to handle lifecycle management. So we may want from Linux to be able to manage this lifecycle. Lifecycle means does this processor is already started by another component. It may be the early bootloader which already runs this component and firmware. But if we want from Linux, we can already start it. So there is a Linux framework which is called Remote Proc, which allows to handle this coprocessor lifecycle. It allows to load a specific firmware from the file system, so that you can update this firmware over the air like you are used to do for Linux. You can stop a remote processor or attach to an already running remote processor, so a processor which is started by its own or by the early bootloader of untrusted firmware, for example. This Linux framework also allows to initiate shared memory for communication and get the debug trace from the debug file system, but it's really convenient, at least for debugging. Let's have a look at the sys file system interface about the remote proc, which allow to specify which firmware we want to boot on this coprocessor, and how to start or to stop it. So it's accessible from the sys file system. That's it. So what you can currently do with the software we did for Zephyr and to make Renesas R-Car Gen 3 running on Zephyr. At the moment, on our GitHub repository, you can send and receive keyframe, you can read and write to an expressly device, you can use GPIO, and you can also start your firmware from Linux, as we just saw in previous slide. You can, of course, communicate with AGL. So we just give a few hints if you want to try it, how to fetch and compile or source code. So current work, our main goal is to go for Zephyr mainline, so that our Renesas work will be available for everyone and maintained following the Zephyr management schedule. We already did the support for the Cortex R7 processor. Our board integration is pull requested, so it's just a matter of day or week to have it in the Zephyr tree. We're also working, as I explained, about integration of the binder over OpenAMP to be able to communicate between Linux and a coprocessor. And all of this work with in mind the end-to-end security to propagate this security strategy we have in AGL framework from the real-time operating system to Linux and then to the cloud. So thank you. If you have any question, don't hesitate. Thank you.